Okay, Peng, I think, are you ready to go?
Yes.
Yeah, okay, so let's get started with this session 4. We have 3 speakers. The first talk will be given by Dr. Peng Zhang, multiple topological states, topological superconductivity, and Majorana modes in ion-based superconductors. Peng, please take it over.
Okay. Okay, thank you. Thanks for all the organizers. Hello, everyone. My name is Peng Zhang. Now I'm working in the University of Tokyo. Later this year, I will join Nanjing University in China. Today, I will talk about multiple topological states, topological superconductivity, and Majorana modes in iron-based superconductors. This is the outline of my talk. First, I will briefly introduce some background. Then I will talk about multiple topological states in iron-based superconductors. At last, I would like to discuss what kind of Majorana modes do we expect in iron-based superconductors and how do we probe them. In this slide, I simply compare topological insulator and topological superconductor. From the concept of topology, they are basically the same. For topological insulator, the gap is the band gap coming from spin-orbit coupling. But for the topological superconductor, the gap is the superconducting gap. Due to the particle-hole mixing in a superconductor, the edge states in the topological superconductor satisfies the property of Majorana Fermi in high-energy physics. So we generally call the edge state Majorana quasi-particle or simply Majorana Fermi. For the zero-dimensional Majorana states, the Majorana bond states, they follow non-abelian statistics, which provides a simple platform to realize topological quantum computation. So recently, it attracts a lot of interest. But we know that in nature, intrinsic topological superconductor is very rare. In 2008, Fu and Kim proposed that if we put S-wave superconductor and topological insulator together to make a heterostructure, then at the interface, the topological insulator the surface state of the topological insulator will open S-wave gap. This state resembles P-wave topological superconductor and is able to host Majorana states in the Vortex cores. But for this proposal, we know that it's difficult to fabricate heterostructure, and the heterostructure is difficult for many techniques to do measurement. Also, this proximity effect can only take effect to the surface state. It's difficult to get homogeneous induced superconductivity for the bulk bands. We know that there are also many interesting topological bulk bands like dioxide metal, wire metal. These topological states cannot be induced to a topological superconductivity with this method. If we can find a superconductor which intrinsically hosts different topological states, then we can naturally combine these topological states and superconductivity, which may provide a very simple way to realize different topological states. That's what we found in iron-based superconductors. This is a simple band structure for the iron-based superconductors. The band structure near Fermi level mainly comes from iron 3,2D, from the iron arsenic or iron selenide layer. Before, people mainly resolved the 3T2G d orbital bands near gamma point. In 2014 and 2015, we started to realize that there may be topological states in this material, in the material of iron, tellurium, selenium. In the calculations, we found that there is a PZ band going down from gamma point to a Z point along the gamma Z direction. The key is that the PZ band has a minus parity, while the three T2G d orbital bands have plus parity. So when they cross, there will be a band inversion. For the bottom for the bottom crossing, there is an SOC gap opening, so it forms a topological insulator state. For the middle crossing, the crossing is protected by the fourfold rotation symmetry, so it forms a Dirac metal state. At the same time, we found some evidence of the PZ band. We doped the iron, tellurium, selenium with potassium, and we found an electron band originally above Fermi level, which should be the PZ band. From the KZ measurement, we also see some signature of the PZ band going down from gamma point to Z point, but we cannot directly resolve the surface state at that time. The reason is that the energy scale for this SOC gap is very small. In the calculation, we found it's about 20 millieV, while the energy resolution for most RPS is about 10 millieV. So it's impossible to distinguish this Dirac cone in such a small energy scale. In the University of Tokyo, we have a very high resolution RPS, which can reach a resolution of less than 1 millieV. So with such a high resolution RPS, we can resolve some feature that cannot be resolved by a synchrotron RPS, like for the arsenic Rashba state. So we used this system to study this iron, tellurium, selenium. We directly resolved Dirac cone band structure with a p-polarized light, which is sensitive to p orbital bands. If we change the photon polarization to S, which is sensitive to the dxz orbitals, we only see a parabolic band. So the band structure should be like this. We have a parabolic valence band, and on top of this band, there is a cone structure. We can we can directly resolve this feature from raw data. If we take a closer look at this small region from this raw EDC data, we see that there are two peaks. The lower peak is similar to this, is the parabolic band, and the upper one is the lower Dirac cone. We can also use curvature or second derivative to increase the contrast. Then the data is more clear. The parabolic valence band, dxz valence band, and the lower Dirac cone. Also, this valence band is consistent with the valence band observed with the S-polarized light. So we summarize the band structure here. We have a bulk valence band from DXZ, mainly from DXZ orbital. And on top of this band, we have a cone structure. We also measured the photon energy dependence of this state with a synchrotron. low energy synchrotron. The energy range is from 7 eV to more than 30 eV. But the energy resolution is much worse than our high energy resolution in the lab, high energy RPS in the lab. So we cannot distinguish the details of this cone structure. But at least we see that this state exists for all the photon energies we measured. So this suggests the surface origin of this cone structure. A more direct method to confirm this surface origin of this cone structure is the spin polarization measurement. Actually, this is the most difficult experiment in this project. Since the spin polarized RPS, the efficiency is very low. It took me more than half a year to optimize the energy resolution and to figure out the proper configuration. At last, I found clear data. We see that near Fermi level, there are spin polarized states. At slightly higher bending energies, there is no obvious spin polarization. For this spin polarization, it switches sign from below the Dirac point to above the Dirac point, from the left side to the right side. So this is consistent with the surface, the spin polarization of the topological surface state. So confirming its surface nature. The last piece for topological superconductivity would be the S-wave superconducting gap of the surface state. This should be easy to understand, since we know that iron-based superconductor is has a S-wave gap in the bulk, so the surface should naturally also have S-wave gap. Indeed, we focus on this small surface from surface, and we observe no obvious isotropy for the gap. Then we conclude from the Fouquet model that iron-based superconductor, the surface of iron-based superconductor is topologically superconducting. Besides iron tellurium, selenium, we also checked other structures of iron-based superconductor. We found that lithium iron arsenic is another promising material. In the theory calculations, we see that this band inversion of the PZ band and d orbital bands is very obvious. In the experiment, we first checked lithium iron arsenic with 3% cobalt doping. We can directly see the 1 Dirac cone. But if we look closer, look carefully to this data, we see there seems another Dirac cone above Fermi level. So we remove the Fermi function of this raw data, and indeed we observe another Dirac cone. And we compared with the calculation, we find the lower one is the topological surface Dirac cone, and the top one is from the Dirac semi-metal cone. Also, it's very easy to dope lithium iron arsenic with more cobalt. So we further checked 9% cobalt doping. In this data, without any other process, we can clearly resolve the 2 Dirac cones. The lower one is the surface Dirac cone. The top one is the bulk Dirac cone. This data, if we compare with the calculation, they are basically the same. We also checked the spin polarization of the 2 Dirac cones, and we found the spin polarization is consistent with the with a simple KP model. We also go back to the topological Dirac metal state in iron, tellurium, selenium. Since this Dirac cone, the bulk Dirac cone is above Fermi level, we cannot directly resolve it from RPS, but we found some indirect evidence. First, we found that the DYZ band, which should be a bulk band, but we see some partial spin polarization. We found that this spin polarization should be induced by this cone structure. Also, we measured the magnetoresistance of this material, and we found a very good linear magnetoresistance up to 30 Tesla, which also suggests the existence of bulk Dirac cone in this material. Okay, in the last part, let's discuss what kind of Majorana modes can we expect and how do we probe them. In this slide, I summarize what kind of topological superconducting states can we have. So we have two different topological states in this material: topological insulator state corresponding to a surface Dirac cone, and topological Dirac metal state corresponding to a bulk Dirac cone. So which, if we can shift the Fermi level, for example, if the Fermi level locates near the surface Dirac cone, then the physical property will mainly dominate by this surface Dirac cone. If we can shift the Fermi level to the bulk Dirac cone, then the property, physical property, will be mainly dominated by the bulk Dirac cone. So if the Fermi level is located near the surface Dirac cone, then in the superconducting state, we will have a surface topological superconductivity according to a Foucault model. Also, if we dope the material to put the Fermi level near the bulk Dirac cone, since this bulk band structure may affect pairing, so in this case, we need to discuss different pairing. If the interorbital pairing dominates, then the gap will be S-wave, similar to normal iron-based superconductors. Then on the set surface, we know there will be a Fermi arc for Dirac metal. Then this set surface will be topologically superconducting, same as the Foucault model. But in this paper, the authors found that for topological Dirac metal, there is some special orbital pattern because of this PD hybridization near the Dirac point. Then this orbital pattern will favor interorbital pairing. In this case, we can expect the nodal gap along the KZ direction. It's a triplet pairing. And on the side surface, at the side surface, we will have Majorana flat bands. From this different topological superconducting state, we can expect different Majorana modes. For this topological insulator plus S-wave superconductivity case, first we expect Majorana bond states in the vortices. Also, if we can deposit a magnetic domain on top of this material, then we can expect Majorana chiral modes along the domain edge. People also propose that there is Majorana hinge modes in this material. If the Fermi level locates near the bulk Dirac band, in case of this S-wave superconductivity, we will have helical Majorana modes along the vortex line. in case of triplet pairing, we will have Majorana flat bands at the side surface. How do we probe this Majorana mode from experiments? For this topological insulator plus S-wave case, the ideal material would be iron, tellurium, selenium, since we see from the band structure that the Fermi level the Fermi level locates very close to the surface Dirac point, so which is a very good scenario. Very good scenario for the Fouquet model. For the parent lithium iron arsenic, it's not a very good candidate because in the experiment I found that the Fermi level lies in between the two Dirac cones. It does not cross any of them. So if we want to study this topological insulator plus S-wave case, we need to shift the Fermi level down to cross the surface Dirac cone. There are already many experiments on these Majorana bond states in the Vortex cores. People observed well-defined sharp zero base peak in the Vortex cores. It has some very special property which can only be explained by the Majorana states. Also, some group they observe some evidence of the helicos, one-dimensional Majorana states in this material. For example, in this paper, people observe some signature along the domain edge. They observe the constant density of states inside the superconducting gap, which most likely comes from the one-dimensional Majorana states. In this paper, people observe some zero base peak in the transport measurement. Also, there are some proposals to detect the chiral states with the transport measurement. In this geometry, if we flow current in different direction, we will see some difference due to the chirality of these Majorana states. For the superconducting Dirac semi-metal case, the ideal material will be electron-doped iron, tellurium, selenium. We need to electron dope this material to shift the Fermi level to cross the bulk Dirac cone, or we can study lithium iron arsenic with cobalt doping. We see that with 9% cobalt doping, the Fermi level lies very close to the bulk Dirac cone. For the superconducting topological Dirac semi-metal, if it's S-wave, then we expect Majorana modes along the vortex line. We may see some signal from thermal conductivity. We will see linear temperature dependence and linear magnetic field dependence. If it's triplet pairing, then due to the nodal gap and the flat band, we may see some evidence from NMR, penetration depth, STM, or tunneling junction for this flat band. Okay, these are my collaborators. Without their help, it's impossible to finish this project. Okay, that's all. Thank you.
Thank you very much. It was a very nice talk. Any questions, comments?
I have one question.
Yeah. Go for it.
Hi, thanks for a nice talk. If you were to go to your previous slide,
yes,
where you proposed certain techniques to probe, if you go to your previous slide.
Yes.
The one like right before the conclusion. I was wondering if you propose some of these bulk probes that are proposed to detect these modes, but somehow I got an impression that these modes are only existing on the surface or the boundaries. Do you think they can actually give dominant signatures?
Which one? You mean
like thermal conductivity or NMR?
Yeah, this is not surface topological superconductivity. It's the it is the bulk Dirac band becomes superconducting. So it's a bulk topological superconductivity. Then we need the bulk measurement.
Okay, I see. Sorry, I was confused earlier. Thanks.
Yeah, it's more than surface topological superconductivity. But but it's true that there is no experiment yet. It's very difficult.
Got it.
Any other questions or comments? Maybe I can have a question. So in the morning session, morning of here, we had some discussions about how much evidence there is for the banding inversion in the bulk. And so with that in mind, could you get back to that RPS spectrum, which shows the valence band stopping at, this one. So I was wondering, if I ignore the surface states for a moment, just to think about the bulk spectrum.
Yeah.
And you said that this valence band is primarily dxz, dyz, is that right?
Yes.
Now, and so this is maybe a question for both you and other RPS folks in the audience. I always thought that the dxz, where is this? Is this near gamma or is it near z?
It's, we don't know. Actually, it's maybe some, you cannot think it as a special KZ. Maybe it's some averaging of some KZ.
Right, but if it's averaging, then it would pick up near gamma, for instance, contributions.
I mean, yeah, you can think of this one. So if you think it's, I mean, the for lithium iron arsenic, this is lithium iron arsenic is more clear. So you see this band, this is clearly a DYZ band, but it does not cross from level. It's
no, I understand.
Kind of...
in lithium iron arsenic, I'm more familiar with without cobalt doping, and I agree with you, that's the case. But can we get back to FETSE?
Yeah, but also, I mean, here you can see in the calculation, it's actually a KZ broadened. So maybe we are picking not a single KZ experiment.
No, but
here, maybe also the case.
Can you just get back to that slide, please?
Yeah.
So I'm just wondering, have you looked at the photon energy dependent, etc.? And because we know at least some part of KZ, the DXZ, DYZ do cross the Fermi energy, and there's a Fermi surface associated with that, right? And do you see it or you don't see it?
We basically see this. This is the photon energy dependence. We see not much change for this DXZ band.
So it never has a Fermi surface?
For this DXZ band. But I mean, after band inversion, it's...
No, I understand. I mean that because the above Fermi energy states RPS doesn't really see it, right? So so the band inversion a bit harder to determine. I just want to understand the RPS that I'm familiar with does have Fermi pockets near gamma associated with DXZ, DYZ band. So maybe again the question, since it's part of discussion, to you and to the other RPS specialists. Is there, is everybody agreeing that that's the dispersion that one should see, or is there some discussion to be made?
So I don't understand your question. So you mean at Z point, we should see two Fermi surface? Is that the case?
No, near gamma, I think maybe, I
no,
think
near gamma, I think the DXZ band is below Fermi level.
Really?
Yeah, DXZ for the 1-1 system. Iron selenium also below
No,
Fermi level.
yeah, so the 50-50%, there's always a Fermi pockets associated with.
Yes, that's DYZ pocket. The DYZ is here.
Yeah, okay, I see.
Let me comment. I mean, there are two spin orbit split bands. The one that you're looking at on the screen now never crosses the Fermi level. The other one does cross the Fermi level. And then there's the second Fermi surface farther out, which is the DXY band, I think.
Mm-hmm.
But I would ask Peng, I mean,
Yeah.
you put up this this electronic structure calculation, which is where that this one, yeah, where you've got it in the middle, in the upper panel. Your data, where you show the bands as a function of photon energy, doesn't agree with that band structure at all.
Yeah, this one, I mean, shows the, if we look, there is some dispersion, but in this photon energy dependence,
No dispersion.
the dispersion is quite small. But also, Carnegie has a paper claim that because of the hybridization, the DXZ band dispersion along KZ becomes very flat. I think this is consistent with his story.
And it's consistent with that story indeed.
Yeah.
So Peter, can I just make sure that what you said, is that because there's a spin orbit coupling that the DXZ, DYZ have some separation near gamma, and so one of them is forming, crossing the Fermi energy, and the other is not? Am I getting that?
Yeah, that's right.
Mm-hmm.
And then, as I said, there's the third thing, you know, the DXY, which defines a Fermi surface farther out, and out of the range of this experiment at these photon energies, they would never see that.
Okay. Thank you. Any other questions or comments?
Actually, I can probably make a small comment on that previous question. So in the so the smoking gun signature for whether the band is inverted is not really so much whether the band goes up and comes down, but what the orbitals are in that band wave function. And with the polarization with the linear polarization, one is able to resolve what orbitals may or may not be participating in this band. So I think in the work Peter was talking about, we did look at the orbital character of the band which is visible in our tests, and I think we made the claim that the orbital character changes from DYZ to something that is not DYZ, and that in a sense is a signature of band inversion.
Well, it will not be pure DXZ, DYZ after the spin orbit coupling.
Yes, sure. But the weight of DXZ, DYZ shows significant oscillations with KZ or with photon energy. So the positions that the photon energy that you would associate with gamma and the positions that you would the photon energies that you would associate with Z have a significant difference in the weight of the DYZ orbital. which is what you would expect if it was mostly DYZ mixed with some spin orbit coupling, and then it becomes something that is mostly not DYZ because of band inversion.
Maybe I can even follow up on that. So the band inversion is supposed to be between D and the P state. So is the PZ state is ever seen?
Also, I can mention that in lithium iron arsenic, the band inversion is very clear. We observed that. But for this 1,1, it's the PZ band is not did not show a clear dispersion along the in the KZ.
Okay, but where is the PZ band in this?
For lithium iron arsenic, I can
okay,
show.
Yeah,
Only lithium arsenic for iron for the 1,1 system is not that clear.
Well, let me comment on that again. In the Canigald paper that you referenced,
yeah,
the hybridization pushes that tellurium PZ band up above the Fermi level. So
yes. In my experiment, I found it's consistent with that scenario. So yeah, the PZ band just maybe at this point is maybe close to a Fermi level, so we cannot see clearly. But for lithium iron arsenic, we can see the PZ band going down very clearly from gamma point. This is the gamma point, this is Z point. This is the PZ band.
Okay.
Yeah, right.
Okay, thank you.
But in the iron tellurium selenium system, that PZ band is pushed up above the Fermi level, I think.
Yes.
Okay, thank you. I don't see any other questions, so thanks very much, Peng. And let's move on to next talk that will be given by Ding Hu. Okay, so